Welcome to this lecture 7 on linear regression and machine learning in general. We will quickly conclude the Bayesian inference for linear regression and talk about the general form of regularization and alternative regularizers. So our problem was to address overfitting through Bayesian and maximum posterior estimates, or the MAP estimates. And recall that we wanted bounded values of Wi. We got that through the 3 sigma rule for Gaussian distribution. To find a posterior using a Gaussian prior, we did the coefficient matching and invoked the results that we had got before. The additional step that was missing was to substitute for mu 0. The mu 0 was 0, and sigma, or sigma not inverse rather, was lambda I. There's a missing I here. So with these substitutions, what do we get? So sigma naught is 1 upon lambda I, or rather sigma naught inverse is lambda I, mu naught is 0. With these substitutions we get the posterior mean to be the original phi transpose phi matrix. Added to that is a matrix of diagonal entries containing lambda sigma square and all the off diagonal entries 0. So what we have done is added a diagonal matrix to phi transpose phi, inverted the whole thing and multiplied by phi transpose phi. So lambda equal to 0 would actually mean that the maximum likelihood estimate for W is recovered through mu m. Okay, now this is interesting because we're saying that if lambda was 0, if we had very high confidence in the data itself, the precision of the prior was 0, then we just stay with maximum likelihood estimate. But if you're not, if you really feel there is some prior knowledge that the data will benefit from, add a non-zero value of lambda. The general tendency is to club together lambda and sigma square. So the MAP estimate for the Gaussian posterior is nothing but the mean of the posterior mu m. The Bayes estimate is the expected value of weight vector under the posterior, and that again turns out to be mu m. That's the meaning of the mean of Gaussian. It's just by virtue of multivariate Gaussian being the posterior. So summarily, the MAP estimate is obtained in this very interesting form, and it has a covariance matrix associated from the posterior. So MLE is a point estimate. The Bayes estimator and the MAP estimate are both point estimates that you get from the posterior. But how about not using this point estimate? How about being purely Bayesian? How about computing the probability of y given x and data point, data set, folding in all the uncertainty that we had associated with W by virtue of estimation. So basically you don't want to do estimation, you just want to normalize across all values of W. More generally, what does this mean? The right hand column just says what this means in general. If you are looking at probability of x given data, the MLE estimate says, well, don't look at probability of x given data, look at data through the maximum likelihood estimate. Bayes estimator says look at the data through the Bayes estimate or the MAP estimate in the case of MAP. Pure Bayesian says, well, no, I'm not going to look at the data through a particular point. So these are looking at the data through the lens of a point estimate. Here we say I'm going to look at the data directly, no lens. And this can be obtained by applying the Bayes rule. The denominator will involve integrating over all the values of the data. Sorry, because you're looking at probability of theta given d. So this is the posterior, but instead of employing the posterior to find a point estimate, what you do is employ the posterior to find the posterior of the data, the test point on which you want to infer. So p of x given d is nothing but integral over theta of p of x comma theta given d theta. But this turns out to be nothing but integral over theta of p of x given d into probability of theta given d theta. And the reason is x depends on the parameter only through d. So given the data, x and theta are independent. Okay, so what is the form of this predictive distribution for linear regression? So what we do is we look at probability of y given the query point x and the entire data set at once. And recapping from the previous slide, this will involve integral over w of probability of y given x comma data comma w into probability of w given data. Of course, now once you have w, you don't need the data. So y given, so as recall that the query point x only models can be modeled using the weight vector w and not invoking the data necessarily. That's what we see here. So the posterior is very interesting. This distribution is a posterior over the output for a new input point x, and that has mu m transpose phi x, which is nothing but the map estimate for w transpose phi x, that's mean, and it has a variance component. So this is somewhat consistent with intuition that the posterior for a new query point still is centered around a mean which depends on the map estimate. In the process, we've also got handle to the variance of the posterior distribution. Now it turns out that you could get the exact same result by minimizing a sum of the squared error and a penalty term. So this particular objective is called a penalized or regularized squared loss. And the intuition is the same as before. You're just discouraging or stopping coefficients from becoming too large, but you're doing that directly without any probabilistic interpretation. But it turns out that the Bayes and map estimate for linear regression coincide with this regularized ridge regression, and you can show that by basically invoking optimization principles and setting the gradient of this objective to 0. The general form of penalized regularized least squares problem is take the squared error as before, and add a penalty term, a lambda times penalty term, lambda omega w. Now this omega w could be norm W square, that's the case of ridge regression or Bayesian linear regression with Gaussian prior, as we have seen. This is the Gaussian prior case. But it could also be different. You could have a lasso regularizer. What does this lasso mean? It's basically looking at sum of absolute values of W vector, and you would like this to be penalized or be as small as possible. Now this corresponds to some prior distribution which we won't discuss right now, which is slightly more messy to handle than what we've seen. You could also have other regularizers such as support based penalty. This basically returns the number of non-zero components in the W vector. So basically you might want the number of non-zero weights to be as small as possible, or in other words you want to select as few features as possible. This is basically the feature selection model. So some of these omegas could be expressed in priors, that can be in closed form. However, some might not be easy to handle but give good working solution. For example, lasso. You can actually write algorithms to find the lasso solution. The support based penalty is a lot more unwieldy. It turns out that you could also express the same solution in slightly different form, or called the constrained regularized least square problem, where you have the least square objective as before, but you embed your regularization into the constraint, and the constraint says that omega W should be less than or equal to theta. Now it turns out that for a choice of theta there will be a corresponding lambda, and for a lambda there will be a corresponding theta, such that you get the exact same solutions for these correspondences. But this proof of equivalence requires tools of optimization and duality, and in subsequent lectures we'll post this as a practice problem. So you could consider polynomial regression with all these different kinds of regularizations, and here's an example degree 3 polynomial regression model. And as we expect with increasing values of lambda, for example in the ridge regression case, we would get less curvature. So if for some polynomial regression choice, if these curves, the bend curves, correspond to unnormalized or unpenalized regression, then with the lambda penalty you could get smoother values of this curve. What actually happens is that the eigenvalues of phi transpose phi plus lambda I are indicative of the curvature. So the eigenvalues of phi transpose phi plus lambda I can be proved to be always greater than the eigenvalues of phi transpose phi alone. So what basically happens is, when you look at the inverse matrix, increasing the eigenvalues reduces the curvature, because the inverse corresponds to something that was obtained for the linear equality to solve for W. More about this when we talk about Hessian and optimization. But moment back to these different formulations, do closed form solutions always exist? We found closed form solution for linear regression and ridge regression. How about lasso L1 norm? And how about the L0 norm? So all this requires tools from optimization and duality. You don't have closed form solutions for these, but you could develop iterative algorithms to solve these. So talking of lasso, why is that interesting? Well, if you look at the level curves for the L2 norm, so let's say L2 norm is constant theta, these level curves would correspond to circles. But let's consider lasso, and let's consider the level curves for lasso. So you'll find that the level curves for lasso have these corners, and in fact in 2 dimensions these are the corners, but in higher dimensions you have lots of corners. So with increasing number of corners, what also happens is the chances of solutions with significant number of components of W to be 0, the chances of this increase, which means you'll have sparser W solutions. You'll have sparser solutions when you put constraints such as norm of W is less than equal to theta. One norm of W is less than equal to theta. In the next class, before we move on to optimization principles, we'll consider one more interesting formulation of linear regression, basically an objective that looks at maximizing the separating surface between the points that you are regressing on and the regression curve itself. That's the topic of support vector regression. Thank you.